So we have a fair idea of what an intrinsic semiconductor is all about and its electrical behavior. Huh? Now we have a more useful variety of semiconductors, which is extrinsic semiconductors. Extrinsic semiconductors. So what we do to an intrinsic semiconductor is we add impurities to the intrinsic semiconductor. We add impurities to the intrinsic semiconductor, and when we add impurities to an intrinsic semiconductor, we produce what's called an extrinsic semiconductor obtained out of adding impurities. To attain a certain electrical behavior, This process of adding impurities is called doping. And the impurities that are added, that impurity is referred to as a dopant. This process of adding impurities is called doping. Now, again, the doping levels are low. The doping levels are really low. Low doping levels. In the sense that, we have an intrinsic semiconductor, which is all identical atoms. We add an alien to that set. Which is an impurity. But not to the extent that it will significantly affect the energy band diagram of the intrinsic semiconductor. We add only to the extent these impurities are added like almost roughly of the order of 1 part per million. 1 part per million? Which means, say, I have 1 cc of silicon at room temperature, and I told you that it contains 10 to power 22 silicon atoms. It contains 10 to power 22 silicon atoms, right? And when I say 1 part per million, you know million is 10 to power 6, right? That means this impurity is 1 impurity atom for 1 million silicon atoms. So low level of impurity for every 1 million, is how much? 10 to power 6 is a million. 10 to power 6 is a million, right? So 1 million silicon atoms would be doped with 1 impure atom, right? That means low level of doping, right? 1 impure atom would be surrounded by 1 million silicon atoms. 1 impure atom would be surrounded by 1 million silicon atoms. That is what it would be. Now, what are the various things that we do in doping, for example? Of course, this doping levels could vary based on applications, right? But this is a rough idea of the numbers. Now, one kind of doping is where we have a silicon crystal and so on and so forth. Silicon crystal. What we do is, and I'm not going to discuss how that is done, that's part of engineering. So, some of these silicon atoms are replaced by the impure atoms, are replaced by some other atoms. So, this becomes an impure lattice. It becomes an impure lattice, a doped lattice, a doped lattice. So, obviously, you know, only 1 in 1 million silicon atoms would be replaced. Only 1 in 1 million silicon atoms would be replaced. There are, the other thing is, whatever we replace this silicon atom with, of course, not too many of these silicon atoms are replaced. I said 1 in 1 million. The size of that atom should be roughly very close to the size of the silicon atom, right? That's when, you know, it would make geometrical sense in the crystal lattice, right? Which means, you know, I would have to look at silicon is group 14. Silicon is group 14. And we will look at neighboring groups, group 13 and group 15 would be neighboring groups which would have similar sizes, of atoms, almost like silicon atoms, right? Group 13 and group 15 would be the dopants, So, when I talk of group 13, these fellows, elements of group 13 would be referred to as trivalent impurities, right? They have 3 electrons in their outermost shell, right? Group 13 would be trivalent impurities. Trivalent, right? One dopant in the group 13 that could be used is boron. And it has 3 electrons in its valence shell. That's group 13, right? So that could be one dopant. Right? 3 electrons in its outermost orbit. Now, when this boron atom, right, replaces a silicon atom in the crystal lattice, so this was my boron, right? And it replaced this silicon atom, for example. Then the 3 electrons that it has would have covalently bonded with 3 silicon atoms. Yes or no? Right? And now there is this nearby silicon atom, which originally was in a covalence with this silicon, now has a deficit, right? It doesn't get the right number of electrons. That means this is, in this arrangement of this boron atom then is like an absence of electron, and therefore it can be treated like a hole. It's a hole. Its energy will belong, let me tell you, the original, for the intrinsic semiconductor, and I'm talking of the same temperature, let's say room temperature, this was my valence band VB. Right? Intrinsic semiconductor, I'm talking of the pure semiconductor. This was my valence band, and this was my conduction band. There were some electrons that were there in the conduction band, and there were some holes left over in the valence band. Now, by adding these impurities, 1 part per million. That's really abysmally small. 1 part per million. For every million silicon atoms, I have added only 1 boron atom, which is not too much. This energy band diagram will not get significantly affected. This energy band diagram will not get significantly affected. Let me draw a bigger view of the same. So whatever you saw in terms of the energy band diagram in the intrinsic semiconductor, you're going to see almost the same energy band diagram in this extrinsic semiconductor, in which I have added a trivalent impurity, to the tune of 1 part per million, right? So this is my valence band, this is my conduction band, almost like what it was in a intrinsic semiconductor. Almost like what it was in a intrinsic semiconductor. And now I have this guy, right? So there is absence of electron in this boron, right? It could take, first of all, let me tell you that the energy level of this position, of the boron impurity, boron atom, is slightly more than the valence band, Acceptor level. This is called the acceptor level. It can accept an electron. That's why the level of energy here is called an acceptor level of energy. Acceptor level. The energy level in this vacant site is an acceptor level of energy, right? And it is just slightly above the conduction band. Now, nearby silicon atoms in the lattice, covalently bonded, have their electrons that belong to the valence band, And some of these electrons can get slightly agitated, slightly energized. And if some electron in the valence band, which are these covalent bonds, they will not find it too difficult to migrate to this level, right? Some electron in the valence band will not find it too difficult to migrate to the acceptor level, because the difference in energies is really small, right? So which means, this absence of electrons, very conducive for some other electrons in the valence band to come and occupy, right? So eventually some electron will come and occupy this space, and there is going to be a hole left behind. Then some other electron will come and occupy this space. This hole will get consumed, but there will be a hole somewhere else. But no matter what, eventually there will be one hole in the lattice. Somewhere there will be one hole left out in the lattice. And for every boron atom that I dope it with, there would be one hole produced. For every boron atom that I dope it with, there would be certainly one hole produced, right? So there were already, certain number of, in the intrinsic, there were certain number of holes and there were certain number of electrons. And now there would be a surge in the number of holes. Right? The number of electrons and holes were equal in intrinsic. But now with this doping, there would be a surge in the number of holes. So holes will now become significantly more. In the doped lattice, compared to the intrinsic, there would be a significant growth in the number of holes. And what I'll show you, I'm going to do a computation later on, but we'll be able to show that the number of electrons that there were in intrinsic, they will significantly decrease. When I dope it with boron atoms, we'll be able to show that the number of electrons will dip significantly. Number of electrons in the conduction band, if they were, let's say, 100, it might become, let's say, much less, right? The number of holes compared to the intrinsic counterpart would significantly grow. Would significantly grow. We'll do that calculation, but let's qualitatively understand things first, right? This will happen. And now we have sumptuous number of holes and very few electrons in the conduction band. Very few electrons in the conduction band, but significantly large number of holes in the valence band, right? Which means great many holes produced here by doping it with a trivalent impurity, and the additional number of holes produced would be the number of boron atoms. There already were certain number of holes in the intrinsic. There are additional number of holes produced. How many additional? The number of boron atoms I have doped it with would be the number of additional holes, would be the additional holes, right? Holes would have increased, and again, you know, I could have taken elements of group 12. See, my idea is now to have many more holes compared to electrons. My idea is to have many more. And like I said, every boron atom which is doped has produced one hole. The number of additional holes will be the number of boron atoms that I have doped the crystal with, right? Question is, I've taken elements of group 13. I've taken elements of group 13, and that has produced one hole. Every boron atom, let's say, would have produced one hole. But if I would have taken elements of group 12, there could have been two holes. So why have I not preferred that? One, of course, size. The other thing is, the acceptor level here is very close to the valence band. But if I take elements of group 12, the acceptor level would be much higher than the valence band, and I'll not be able to do what I wanted to do, right? It'll not. So eventually, right? So then group 13 therefore is obviously the one that is used compared to group 12 to produce extra holes. So now there is, all hell breaks loose. Great number of holes, fewer number of electrons in the conduction band. This is a semiconductor in place then. This is a semiconductor in place. In fact, and this is at the same temperature. This extrinsic is at the same temperature as its corresponding intrinsic before doping. And the rate of regeneration, whether I talk of extrinsic or I talk of intrinsic, rate of thermal generation, in both cases will be the same function of temperature. So the Ft that I use for intrinsic will be the same as the Ft that I use for extrinsic thermal generation. And the rate of now number of holes and number of electrons are not equal. Number of holes much larger than number of electrons, much larger than number of electrons, right? now this Ft was the rate of thermal generation in intrinsic. This same number would be the rate of thermal generation in extrinsic. Same thing, because the doping levels will not affect that significantly, right? Now, I have different number of holes and electrons. Rate of recombination would be what? Rate of recombination would be K times number of electrons into number of holes. That's a rate at which whole electron pairs are getting destroyed. That will be proportional to number of holes into number of electrons, right? Now, this is what happens. But realize that the same number was true for intrinsic semiconductors. And intrinsic, this number was also K times Ni squared. That means this would be K times Ni squared also. Which means Na into Nh will remain constant. Number of electrons into number of holes. For whatever migration I do, intrinsic to extrinsic or whatever, number of electrons into number of holes will be square of the corresponding intrinsic particles. Intrinsic particle is a fundamental property of that matter. If I take the same volume, At the same temperature for a given piece of matter, this Ni is a unique number. It's a property, right? And this happens after doping. This Ne into Nh will be always equal to Ni squared. I change the level of doping, then the number of holes and number of electrons will change. But this product will always remain equal to Ni squared. So Ne into Nh is Ni squared is very fundamental to semiconductor electronics, right? The product of number of electrons into number of holes will remain a constant Ni squared. So tomorrow I change it to Ne prime and Nh prime, then Ne into Nh would be Ne prime into Nh prime. This is what would happen. That's cardinal, right? Now, this kind of a doping of an intrinsic semiconductor with a trivalent atom, with a trivalent impurity belonging to group 13, has now created large number of holes, which behave like positive charges, on application of an electric field, This kind of a semiconductor produced is called a p-type semiconductor. P-type extrinsic. This is called p-type extrinsic. It's called a p-type extrinsic semiconductor. P is about positive and many more holes than electrons, right? And holes behave like positive charges. That's why it's called a p-type semiconductor. That's the reason it's referred to as a p-type semiconductor. Clear? Now, so essentially, you know, when you take a p-type crystal, when you take a p-type crystal, when you take a p-type crystal, a typical representation of that crystal will be, see, when these boron atoms accept an electron, they become like a negative boron ion. Right? And these fellows, these boron ions are immobile. They are immobile. But the holes move. The holes give you an effect of movement as if they were positive charges, right? So how we represent a p-type crystal? Is, so this is the dopant, which is like negative. This is only a representation. And so on and so forth. Negative boron ion. And so on and so forth. And with every boron atom that I have doped it with, I am going to locate a hole in the lattice, right? So what I do is, it's not like this hole is present here, it's a representation. So there is going to be holes. There would be these holes. There are these holes. Boron ions that are negatively charged, and there are holes created. Number of holes will be equal to number of boron ions, right? I'm not showing silicon here at all. For sure, these boron ions, boron atoms, they are immobile. But these holes give you the effect of movement, as if they were positive charges. So then, in this, large number of holes produced in a p-type, depending on the extent of doping, large number of holes produced, right? And very few electrons in the conduction band. So this is large number of holes. Very few electrons in the conduction band. Very few electrons in the conduction band. These holes behave like positive charge carriers. Don't think that they are positive charge carriers, but they behave like positive charge carriers. right? And so they are like, we will call them charge carriers only, right? As if they are positive charge carriers. Much more than the number of electrons. These holes are then referred to as majority charge carriers. For a p-type, they are called majority charge carriers. They are majority charge carriers. And these electrons that are very few in number, they, there are traces of these electrons. They will have the same space. They will have different energy levels. There are traces of these electrons in the conduction band. This is an electron in the conduction band. This is another electron in the conduction band. This is another electron. This is another electron. So this whole place is replete with a large number of holes and very few electrons in the conduction band. The holes are majority charge carriers. The electrons in the conduction band that you see wandering in this lattice, they are minority charge carriers. These electrons are minority charge carriers. They are minority charge carriers. So in a p-type semiconductor, the majority charge carriers are holes and minority charge carriers are electrons that belong to the conduction band. Right? That's a p-type semiconductor. That's a p-type semiconductor. Right? Now, and how have we produced a p-type semiconductor? By doping an intrinsic semiconductor with a trivalent impurity. A trivalent impurity belongs to group 13. Boron for some reason is preferred, right? And the extent of doping is of the order of a part per million. For every million silicon atoms, you will find maybe one impure atom, the boron atom, right? It has produced excess number of holes and has decreased the number of electrons over and above what you saw in the intrinsic type. And this mass law of action, this is called mass law of action. No matter what I do, I started with this arrangement, K times Ni squared. Rate of recombination of rate of thermal generation equal to K times Ni squared. And if Ne and NH change, but this product will remain the same for a given piece of matter. Number of electrons in the conduction band into number of holes in the valence band will always be Ni squared. That's a fundamental law. Now, so one kind of doping then. This is one kind of doping producing what is called a p-type crystal, p-type semiconductor, a p-type crystal. There is another type of doping that can take place to produce another variety of extrinsic semiconductors. Can I wipe this off? Intrinsic is pure, extrinsic is doped or impure. Can I wipe this off? Another extrinsic semiconductor is mass law of action. Some people call it law of mass action. Does not matter. Na into NH will be Ni squared. That's the important thing. Call it any law. Right? Extrinsic semiconductor p-type we have seen. Now, again, the lattice right? Silicon crystal lattice, intrinsic. Now when I replace some of these silicon atoms, only one in every million silicon atoms would be replaced. There is a process of doing it. Sometimes what happens is in a lattice there is what is also called a lattice defect, in which there was the silicon atom itself missing. Then the impure atom can come and occupy this position. There are other ways of diffusing impurities into the intrinsic semiconductor, but we'll not bother about all of that right now. But whatever be it, another kind of doping that we will examine is that on an average, when 1 in a million silicon atoms is doped with a pentavalent impurity, pentavalent means what? How many electrons in the outermost orbit? 5, right? That's a pentavalent impurity. 4, and this is the 5th electron in the outermost orbit. That's a pentavalent impurity. And which group of the periodic table? Group 15. Group 15 of the periodic table. One preferred element in group 15 is phosphorus. Phosphorus. It has 5 electrons in its valence shell. It has 5 electrons in its valence shell. Now, when this, again, like I said, by doping this, I'm not going to significantly alter the energy band of the intrinsic. The energy band will not get significantly affected because only 1 in 1 million silicon atoms would be replaced by a phosphorus atom, which is a pentavalent impurity. Now, when this guy comes in and with a certain mechanism, it replaces this silicon atom. It replaces, let's say, this silicon atom. What transpires? The following happens. Phosphorus and there is a 5th electron. See, the 4 electrons, they would have neatly bonded, covalently bonded with 4 silicon atoms, right? The 4 electrons, 1, 2, 3, 4, would have covalently bonded with nearby silicon atoms to acquire the stable octet. Now, there is an additional electron here. There is an additional electron here, right? There is an additional electron here. Now, let me tell you that the original energy band diagram for the intrinsic semiconductor was this was my valence band. इसको हटा देते हैं. And this was my conduction band. Okay, this was the conduction band for the intrinsic semiconductor, right? Now, this extra electron, unused electron that you see here, it has a certain energy level. It has a certain energy level. The energy of this electron is slightly less than the lower than the conduction band. The energy of this electron is slightly lower than that of the conduction band. That means this is the energy level of this electron. Slightly lower than the conduction band. And this gap that you see is roughly of the order of 0.01 electron volt, which is very low. It's only roughly 0.01 electron volts lower than the conduction band. Now, with slightest of excitation and agitation, this electron whose energy is here can easily migrate to the conduction band. Right? This electron, right, which is available now, can easily migrate to the conduction band. Yes or no? Right? So this electron, so which means every phosphorus atom then can donate to this system an electron belonging to the conduction band. Yes or no? Every phosphorus atom has an additional electron, unused electron, whose energy is only slightly less than that of the conduction band. With little bit of excitation, little bit of thermal agitation, this electron can go on to the conduction band. This electron can go on to the conduction band. Which means for every phosphorus atom that I have doped it with, for every phosphorus atom that I have created this doping with, there is an electron that I have donated to the conduction band. Every phosphorus atom would have donated one electron to the conduction band. Yes or no? The number of additional electrons that would now come to the conduction band would be the number of phosphorus atoms I have doped it with. Right? So if I have doped it with 1 million phosphorus atoms, yes, if I have doped it with 1 million phosphorus atoms, I would have additional 1 million electrons belonging to the conduction band. Right? So now in this arrangement, quickly, sit down. So number of additional electrons now coming to the conduction band. There already were some electrons and holes in the intrinsic. There are now additional electrons that have come out of every phosphorus atom, right? So then you would see a surge in the electrons in this arrangement. You would see a great amount of surge of electrons belonging to the conduction band after you dope it with phosphorus atoms, after you dope it with a pentavalent impurity. Number of electrons in the conduction band would grow significantly, and number of holes that originally were, if there were a certain number of holes originally, then the number of holes will decrease. Number of holes will decrease to maintain Na into NH a constant, to maintain Na into NH a constant. Holes will obviously be present in the valence band, electrons in the conduction band, right? So there is a great amount of dip in the number of holes compared to the intrinsic counterpart, right? Now, how we represent this crystal, which is doped with a pentavalent impurity. We never show silicon atoms in a crystal. We show the dopant and we show the charge carriers, right? So now what we have in this kind of an arrangement doped with a pentavalent impurity is, so if this is my crystal, then in that crystal, these phosphorus atoms would have donated an electron. Every please go, not a problem. Every phosphorus atom would have donated an electron migrating to the conduction band. Would be one electron less and then behaves like a positive phosphorus ion. Then behaves like a positive phosphorus ion. It's immobile by the way. Positive phosphorus ion. And every phosphorus ion has donated one electron. So, you know, I put an electron on top of it. That means it has contributed to an electron in the conduction band. And, you know, this is the level at which it donates an electron, right? The energy level of this electron is this. This is the energy level at which it has donated an electron. This is called the donor level. This is called the donor level, which it makes sense should be very close to the conduction band, right? If it was much lower than the conduction band, then it wouldn't have been possible for this electron would have been sedate. It wouldn't have been possible for this electron to move to the conduction band. It would be a useless electron if it can't move to the conduction band, right? So that's the donor level, which is good thing is it's only slightly below the conduction band. So every phosphorus atom after donating becomes a positive phosphorus ion, and its contribution is to the tune of one electron in the conduction band. This is what has happened, right? So this is one phosphorus, another phosphorus. This is just a symbolic representation. Etc. So so a large number of electrons in this arrangement compared to the number of holes, right? electrons then that you see here are majority charge carriers. In this arrangement, electrons are majority charge carriers. But you will also see traces of holes. You would also see traces of holes. So there are some holes in the valence band that you will see. And holes are minority charge carriers in this arrangement. Holes are minority charge carriers. You'll only see some holes. And the energy level of the holes will always be in the valence band. The energy level of the electrons, free electrons, will always be in the conduction band. Right? This is what happens. So, then, many more electrons than holes. This kind of a crystal is called a N-type crystal or a N-type semiconductor. N is for negative. So, N-type semiconductor. It's called a N-type semiconductor, etc. N-type crystal. Majority charge carriers would be electrons here, and minority charge carriers will be holes. Right? Phosphorus ions will be immobile. Like the boron ions were there, immobile, phosphorus ions will be immobile. Right? So, the two type of extrinsic semiconductors that we are going to take care of and in various combinations use would be extrinsic p-type and extrinsic n-type. Extrinsic p-type is doped with trivalent group 13 elements. One is boron, and that will give me majority charge carriers holes, minority charge carriers electrons. That's a p-type semiconductor, extrinsic. And then if the doping is done with pentavalent impurities like phosphorus, then we get an N-type semiconductor in which majority charge carriers would be electrons in the conduction band, and there would be traces of holes which would be minority charge carriers. That's the N-type semiconductor. Right? So two kinds of crystals could be produced, p-type and n-type, depending on what I have used as a dopant. Right?